Hi, everyone. Thank you for being here today, and welcome to meeting number 7 of the M2D2 series. We are very much excited to have Thomas Cauchy sharing his work with us today, his work on EvoMol. A bit more about the speaker before we start. Thomas has been trained as a theoretical molecular chemist and has completed his PhD on molecular magnetism under the supervision of Eliseo Ruiz at the University of Barcelona. He is now assistant professor at the University of Angers in France. With his experimental colleagues, they work on the development of new organic materials, such as organic electronics. For several years, he also has been collaborating with Benoit Damotin of University of Angers as well, on the application of combinatorial optimization and machine learning for molecular chemistry. Thank you, Thomas, for accepting our invitation, and we are looking forward to the talk. Without further ado, your floor is yours.
Thanks very much. Well, first of all, thank you, Prudencio, for this organization of those meetings and this opportunity to allow us to present our work in the de novo generation of organic molecular materials. So it's a collaboration between two labs in Angers, Angers being a middle-sized city in the west of France, in the Loire Valley, and a rich history coming back from before the Romans. And you can see we have a stronghold in the middle of the city. I belong to a multidisciplinary chemist lab where we have 50 permanent people working together, either in modelization, synthesis, characterization, and on components and devices for mainly organic molecular materials or hybrid inorganic-organic. We don't do drug-likes, but we will see what we can do in our method to treat maybe drug-like problems. And for the last years, I've worked a lot with Benoit Damotin in computer science from the Leria laboratory. And most of the results that you see today came from the PhD thesis of Jules Legui, who is present in the chat. So if you have questions, technical questions, Jules can answer them directly in the chat. And if it's a more broad questions, you can interrupt, or I can answer during the meeting. I can see the chat in my second screen. So first, let's define what is a molecular material. It's a material. That means the property of the materials comes essentially from the molecule. That means that we can draw a relationship between the molecular graphs and the material property. Let me show three famous examples. Let's say we are working on electronics. For an electronic conductor, you need a donor of electrons and an acceptor of electrons. For the donor part, and it was the first ever organic conductor ever found in 1972, is the cation form of the tetratiafulvalene. So you see, it is an organosulfur conjugated P system. And still, 50 years later, it's still heavily studied with more than 5,000 articles in the last decade. The thing is that it works well. It's not very soluble, but it works well. But if you don't want to use the tetratiafulvalene, you are more or less stuck with thiophene derivatives, and alternatives are scarce. For the acceptor part, you may find perilene derivatives, this P-conjugated system here substituted by diimides compounds. And if it's not a perilene, you have fullerene derivatives. Again, with a huge research on this part. Finally, third example, if you're searching for photo switches, that means a molecule that is stable at two geometries that are different. Here, for example, the azobenzene, where you have a trans to cis isomery that you can activate upon light absorption. There is a lot of research around azobenzene as photo switches, and if it's not azobenzene, it's DRE latex. So as you can see, in many applications in materials, we have very few good candidates. So our objective is to be able to produce a method that can propose new scaffolds, for example, new compounds that are clearly totally different. As you can see also is that the chemistry in molecular material is not the same as a drug-like. Those are clearly not drug-like compounds. Therefore, the chemical space that we need to explore will be different. And we are not the first and only one to work on such themes. Okay, so we must cite, for example, the work of Alan Aspuruguzik in Canada. Since 2016, they published a mixture between screening guided by machine learning experiment, or 2 years later, a GAN generator to treat such electronic properties problems. Even in these thematics, I need also to clearly shout out the work of Koji Tsuda in Japan, who've produced a Monte Carlo tree search generator based on smiles and called ChemTS that was applied on the absorption, optimization of the absorption wavelengths of compounds. So they've generated compounds that could absorb light at 400, 500, and 600 nanometers. And the beauty of this article is that they've proposed, they have selected with an expert, and they've gone through synthesis to validate the method. So this is really an inspiring work, but we've tackled the same problem differently. Let me show you. First of all, to finish the introductions, let's talk about the chemical space. So you know that the combinatorics is phenomenal, immense, infinite, and there is we are looking for lone stars. The thing is that in molecular materials, since we know very few good candidates, there is probably much less stars than in this picture. And in the space, there is a lot of unsynthesizable combinations. It was one of the questions of Prudenso some seminars ago, how much of the chemical space is stable or not stable, or that we can reach. And clearly it's never been measured. However, doing calculations, we've done a massive amount of calculations. Almost it's an instinct-based approximation, but maybe 2/3 of the combinations are not stable. And in the last third that stands still, there is a lot of those combinations that are useless. That means that there is a huge problem concerning the exploration and how you can score and explore your chemical space when you're looking for few good examples that maybe have a shyness that is very, very local. So the outline of my work of this seminar will be one, to talk about the definition of the objective in our case and in any other case, drug-like. Then I will present EvoMol and what we've chosen to produce as a method. We will discuss along the way the realistic solutions that can be produced with an evolutionary algorithm, since it's one of the key critics of this kind of generation. And finally, I will come back to the problem of our computational costs. The evaluation functions in DFT, in quantum mechanics, is huge. Therefore, we've proposed surrogate-based and BBO approximations, that methods that and I will finish with this part. So let me show you in detail what can be an example. Let's say we want an alternative to, in the organic conducting party, to the tetratiafluvaline. Let's say that since it's a good donor, we need an energy in the highest occupied molecular orbital, the HOMO level, around the same level. That means between -4.5 to -5. And we want the cation state. That means that when we remove an electron, it should be stable and it should stay in this level. That means that the HOMO -1 needs to be at least 2 electrons below to not mix with the HOMO level, and the LUMO level should be relatively high to, again, ensure a stability in the cation. So clearly, for our kind of problems here, we will need quantum mechanics. That means we need to calculate with quantum chemistry such properties. The thing is that, as you can see here for the same molecule, we have 2 electronic diagrams based on the symmetry point group optimization. That means that if the TTF is flat or if it's curved, we see a change in the HOMO level that is quite important, 0.2 electrons, for example. When you define your functions, you should be aware that DFT being an approximation method, that means that we have several approximations depending on the kind of calculations, DFT or not, if depending on your basis set, and depending on your molecule, if its potential energy surface is flat, or if there is several conformers, the electronic properties can differ. So this can be a problem. Furthermore, when you want to then go to a device, you will need, for example, as a conductor, you will need a stacking. That means the molecule needs to stack, and many times it's a p stacking to form a band structure and a conductivity band. However, you do not want to force it flat. C4, that means that you can only explore the chemical space that is flat, for example. And if you want chirality, it cannot be flat. So many times in chemistry, we have those kind of intermediate regions that we are searching that make it very complex to score a compound. Furthermore, when we want to synthesize it, we want it to be soluble, for example, to be able to be processed. And when I've discussed with colleagues, many times will it be cheap? Will it be a green chemistry? And how can you score such criteria? You've seen in the previous seminar that to be able to say if it's synthesizable, it's a good question. If it costs a lot or not, it's even another question. Let's say we have an objective function. We know that we will need quantum mechanics. Formally, that means that we need 3D atomic positions. 3D atomic position is not really an efficient, and it's quite cumbersome representations in terms of informatics. Therefore, we've opted to use a molecular graph approach. And to be sure to have to respect the valency rules, we've chosen the Erdekit annotated molecular graph representation that allow us to be sure that the graph is respects the valency rules. This approximation or this constraint is not is important because when you're looking for complex electronic structures, when you have conjugations, sometimes the double bond or formally single, double, and single is not totally correct. So the thing is that our method works when you can draw a Lewis-like structures. And we avoided any Smythe representations because in this kind of method, that can be some syntax problems. So we've tried on the molecular graphs and we've made a generator in molecular graphs. We are not the first ones and not the only ones. And very recently, at the same time of EvoMol or EvoMol publications, almost, we have the GBGA from Jan Jensen, that is an excellent generator also, based on the Monte Carlo research for the mutations. And there is CREM that works on chemical functions when we work more on an atomic scale. And why did we choose to start from scratch? Is that we wanted to try what are the impact of the mutations, and we wanted to make it very simple, unbiased. That means we've hoped to start with only methane. That means nothing, no previous data, since there is no data set in material chemistry. I will talk about it later. And we've wanted to see if with simple atomic mutations, we could reach and respond to optimization problems in electronic properties. So we've started like that, and the results were quite impressive. That means that it works really nice, and I will show you how. Our mutations are really simple. We can append atom, we can change a bond, remove an atom, substitute an atom, insert a carbon, cut an atom, and move a group. So yeah, it works fine with small molecules, because to be able to build the vitamin B12, for example, it should be very expensive in terms of mutations. However, in Moltec-Anjou, we like to understand the relationship between small molecules and the properties of the material. So it's the kind of chemistry that I like to study. And furthermore, we've wanted it to be interpretable. That means that we keep the history of the mutations, and you will see, we can see by this way the exploration graph and see how it can explore the chemical space. EvoMol is free and open source. You can download it in the GitHub. And Jules, by the way, has at least 6 months again of before the finalization of its PhD. So if you want to try EvoMol and if you have questions, he will have this time to make tweaks for the programs and so on. We don't always start with TTF, by the way. Many times we only work with methane. I will show you. So we start to test our generator with simple benchmark problems. And we've seen for example, synthetic accessibility score. So it was published by Peter Hurtel in 2009, and it's not a score to optimize. The thing is that it was proposed to be able to assess if a molecule, depending in the kind of chemistry that there is in the molecular graphs, that means depending in the chemical functions, if it is present or not in the pubchem, you will have a reward or a penalizations. And if you have two complex cycles, rings, you also have a penalty. Officially, or at the origin, it was a scale from 1, a huge synthesis ability, to 10, inaccessibility. And we've used it in a normalized approach where 0 is unstable and 1 is, we predict it to be very accessible. And we've managed to optimize the SS score. And the beauty of it is that we understand in this kind of simple problems why this is the result. So the best result is a ring of alkyl chains. Why? Because the alkyl substituent is really present in almost all chemistry in the pubchem. Therefore, when you put only alkyls and one single ring, you have the best score ever. So it works great. So then we tackle another benchmark, the QED, very used in drug-like problems. However, the publications was based on a statistical analysis of drugs. That means that they've seen that many drugs have a molecular weight that is between a range, a partition between the octane water partition coefficients, a certain number of hydrogen bonding acceptor and donors, a certain number of rotamers and aromatic rings. And so these values, the QED, is often used as a maximization problem when in fact it should be maximized around 0.6. And in this article, they never went to say that if your molecule has the correct QED, it will be a drug. It's just that if it has a correct QED, it could be or it resembles a drug. And so we've maximized the QED. So it's a little bit stupid, but at least we can see that. And the beauty of an evolutionary algorithm is that it can find the loopholes in your questions. So if you leave free EvoMol, it will find that this NNO ring, 3-member ring, highly unstable. However, there is one hydrogen bonding donor and acceptor, and there is a ring with 6 electrons shared. So for RDKit, this ring is aromatic. So I'm pretty sure that UKL and the RDKit, the people that do this implementation in RDKit never thought about it as an aromatic ring. However, when you ask RDKit, it finds it as an aromatic. Therefore, EvoMol has an incentive to add it in the QED. So what is interesting is that in many optimization problems, when they maximize the QED, they never show the molecules. The thing is that in our publications, we've shown that, and one of the referee just point out that any evolutionary algorithm tends to produce such bullshit. And the thing is that you can tune the evolutionary algorithm to respect some chemistry. So we can add, either by filtering or in the score, we can make an incentive to produce only chemistry that is known in PubChem, in ChemBL. For example, here we have the maximum ever published in the QED, but with respecting a ChemBL score or a synthetic activity score. And you see, therefore, that the molecule is more pleasant, more reasonable. And so evolutionary algorithms, they can find loopholes, and if you leave them free, they will produce strange chemistry. The thing is that you can control it by such filtering. So one of the interesting aspects of EvoMol is that you can produce exploration plots where you have your starting point. So we start from the simplest molecule, methane, and you see how it opens branches by mutations. And when you find good scores, going to the yellow values, you see how we can intensify around those mutations. That means that when he found something that seems to have a huge score, the mutations we tend to favor such chemistry. So he has exploration capacities and intensifications. And to do an equilibrium between the two, we've also published an article showing the role of diversity, maybe to force explorations in different directions. So quite happy of how it was working, we tried to tackle some electronic properties problems. So we've started with the worst possible starting point, methane, because it's the lowest HOMO level and highest LUMO level. And we try to maximize or minimize the LUMO. That means to cross all around the chemical space to search for a maximum in donor and maximum acceptor. That means that there is some limitations because the maximum in HOMO level should be a polymer. So the maximum size of our result should be 9 heavy atoms. And those correspond to the criteria of the reference data sets that are sometimes used in quantum mechanics called QM9. I will present them a little bit later. So in these data sets, there is already published HOMO and LUMO values. And as you can see, -4, for example, is a good result. We start only from methane. We don't give him the data set. And what we see is that comparing what is already known in the data sets, we can do better. That means that the highest HOMO value in the data set is -3.17. And in EvoMol, we can compute an anti-aromatic cyclobutadiene with amino groups. And it's indeed, you see amino groups everywhere, since it's a very effective, efficient electron donating substituents. And of course, the thing is that the cyclobutadiene is not stable. It's an anti-aromatic. However, if we talk about chemistry, what is the best HOMO value at 9 atoms? It is based on this anti-aromatic ring. So the answer is correct. When you limit EvoMol to only chemistry that is possible, or more or less, it's a little bit an exaggeration to say the least, but to limit it to chemistry that is known in ChemBL, you see that he forgot the cycle at 4 and he produced still amino and hydroxyl groups. So it works fine. To the LUMO level, where we want the most accepting group, we see in the best data set that the lowest LUMO is minus 5.74, and it's quite strange. That means in the data set that are published and used as the reference in quantum mechanics, there is strange chemistry with this cycle at 4 with 2 double bonds here and very strange 6 atom rings. EvoMol, free to roam, can be stuck to a strange chemistry also. That means that something that is more mineral, something that looks like a nitric acid with fluorine. So he can be stuck here. And this is a problem when your intensifications, you're intensifying in a group and it's an area that you don't want. Therefore, limiting to a ChemBL chemistry-like, we've avoided these solutions, and we found another chemical group that is very accepting, the carbonyl, and we do a polymer, a Morlos polymer of carbonyls with such compounds. And then again, the referee tend to say those compounds are more or less useless. However, the second one is thought. That means that there is publication concerning the productions in situ, because it is highly reactive, but it can act as a reactant that you produce in situ. So this compound do exist and is studied as a good accepting. So this is a very good answer. And furthermore, lately, with the publication of Zinc 20, they published a very interesting tool where you can draw your compound, or you can put the smiles, and you can search in the Zinc database at a few mutations in the graph if there is already known molecules that do exist. And when I've tried with these best solutions, it does not exist in Zinc. Yes, it is totally unstable. However, there is at 2 mutations away compounds that are quite similar. The last one, for example, do present 3 carbonyl compounds and an hydroxo, and you can buy it. Or if you want to keep the fluorine and you sacrifice 2 carbonyl, you have this kind of structure. So this is one of the aspects that I've learned, that what is in the already published in dataset is not a better chemistry than the one that we can produce. That an evolutionary algorithm can be stuck to unstable areas, but with a simple constraint on chemistry, you can avoid that. However, when you find something that is interesting, you will see intensification in this region. So to compensate that, there is a way to maybe force some diversity and working on this theme, I've learned a lot about chemistry. So one of the main aspects that if you need to recall something today is that there is bias in data, but there is also bias in the experiment knowledge. That means when you ask a scientist if a compound exists, he will, there is no chemist in the world that knows all chemistry. He will have a bias based on his training on the type of chemistry that he do, and many times, if it does not correspond to the chemistry that he knows, it's not chemistry for him, or it's not possible. So, for example, now I show this slide where I present to people that are not in materials or even in materials that you can buy such compounds. This 6-member ring with only carbonyls can be bought. You have this kind of fish-like features, and they are pretty. It's an acid phosphoric, but this one is really nice with the 2-fluorine. And when you see that there is too much cycle imbricated, you can buy a 3-member ring that is with a 5-member ring and a 4-member ring, and there is several of them in zinc. And when someone tell me that the molecule that you can construct is not pretty, I show them this ChemBL molecule that do exist and whose representation is not pretty at all in 2D. So we've addressed the 3 points right now, and I will finish with the BBO and the problem of when your objective function is too costly. That means it can be a drug-like problem. For me, it's electronic computations, but for example, if you do drug-like and you want docking, can you calculate the docking properties of all your generated compounds? Probably not. Therefore, for the electronic, we've tried machine learning. We've seen in 2019, we've seen a boom in neural network predictions. It was following a huge several studies on kernel ridge and GPR, depending on the descriptor. And then in 2017 to up until now, several models based on neural networks, graph neural networks, or different architectures that were published and that show or stipulate that they can do better than DFT. As you can see here, for example, Schut and the Schnedt model officially can predict the HOMO level to 0.04 electron volts. That means better than a simple change in geometry for the same molecule. So very interested, we've tried to reproduce such a results. So the reference database is a QM9, is an extract of the GDB 13, but with only CNOF and up to 9 heavy atoms, the rest being hydrogens. And there is like 130K, 110, depending on how curated you use the dataset. We've trained a neural network Schnedt to predict such HOMO levels, and indeed, we can reproduce the same results. The thing is that we've produced a similar data set that is extracted from the PubChem-QC calculation, that's PubChem molecules, but with only the same atoms and size restrictions. There is, in PC9, there is 80,000 components, so more or less similar in size, but there is only 20K compounds that are similar in both datasets. That means that there is a lot of PubChem that is not in QM9, and there is a lot of generated in the GDB that are not known in the PubChem. And so we were able to test the generalization ability of such models. And the thing is that if you're looking for total energy, HOMO level and LUMO level, they are highly dependent on your chemical environment, chemical functions. And so, for example, there is no peroxo in QM9. So when you ask for the HOMO level of a peroxo, the answer will be very bad. So you can see here in this graph that depending on the number of molecules that present this kind of chemical functions, in rare chemical functions, you can generate a huge error in predictions. And this is very problematic if you want to explore the chemical space, since you will produce molecular graphs that present strange chemistry at some point or rare chemistry, And if you cannot predict correctly the score of the compounds, your surrogate is not efficient. So that's why we first try to produce diversity. So we've wanted to produce the best data set at 9 EV atoms with all the chemistries that we could generate. So we've made an objective function that was the maximization of the Shannon entropy of a data set. And we've tried a Shannon entropy based on the entropy for each functional groups or scaffolds and so on. And since it was a huge computational cost, and because Benoit wanted to produce collaborative research, we've set up a BRINC collaborative project, QChempedia, and we had like 600 benevolent crunchers that calculated more than 1 million of compounds twice. And so thanks to them, thanks to those crunchers, we were able to produce diversity. And if we look at, for example, some key chemistry, we've seen that in QM9, the base chemistry is the carbon chemistry, where they have added some nitrogen and oxygen, but there is a huge lack in heteroatomic chemistry. That means hydrazines, hydroxylamine, aminals, and imines. And the percentage of compounds presenting such functions, you see, are very low in QM9. And we were able to produce much more heteroatomic chemistry. And in terms of electronic properties, we managed to produce new compounds that are more unstable, yes, but that have lower LUMO, for example. And for material chemistry, it was quite interesting. And here we can see that in the blue curve, that is all the molecular graphs that respect valency rules that we could draw, and what was stable after computation, you see a huge decrease. We've lost almost 2/3 of our compounds that are totally unstable by DFT. Does that mean that only valency rules is not enough to assess any stability, for example, in terms of electronic properties? The other conclusion of this work was that we have a problem. That means that the combinatorics in terms of chemistry is phenomenal. If we look at subgraphs, that means the dataset, yes, we've published it in Figshare and with all the log of the calculations. That means everything is possible. The thing is that the dataset is not formatted. You have huge logs, but you can treat them as you want if you want some filtering and so on. But we can talk about it after. So in this dataset, in OD9, even considering only the stable compounds, we see that the shingles, that means the subgraph up to 2 neighbors, in terms of diversity, we've started with a reference dataset with a few thousand to 250,000, and more. Almost half of them are totally unique. It's like in NMR, it's a G4 environment that appears only once in the dataset. For training, this is not very good. And if you want some precision, for example, with R3, the 3-number chemistry, we have a huge amount of totally unique chemical environments. So the perfect data set will probably never exist in any chemistry. So that's why, and I will finish my work, my presentation with that, we've tried to test if learning on the fly, the chemistry that you need is a good approach for material chemistry. Or in a more broader approach, if you have a huge computational cost and you don't want to calculate, or you don't have any huge data set, a surrogate-based black bloc optimization could be interesting. We've started with methane. We've trained a GPR, and we've used a GPR model because the Gaussian form allows for the use of the expected improvement and so an error estimation. So we do some mutations, and we see if these kind of compounds can improve the expected improvements. That means that the BBO is able to go do some diversity, to go in different directions, to have a GPR that can predict more or less what is going on. And you will select either someone that seems promising to have a better GPR or for answering the solution. And we only do the calculations on those compounds. So we've started, and I present here the result of the HOMO maximization without any filter. So because we know what the answer was, and we found that he clearly find the anti-aromatic ring with all nitrogen substituents. So it's even better than EvoMol, much faster than EvoMol. That means that you avoid a lot of calculations. However, this demonstration is for here unconstrained explorations. We don't know if you do too much constraints in the type of chemistry. The thing is that can you go and do mutations only with chemistry that is stable up to the correct solution? So this is one of the key problems that we are assessing right now. And this is a simple problem. The best HOMO, we know that it's many nitrogens. So there is one mutation that have a good score or that have a good impact. However, we have some interesting work in progress concerning the BBO and IDs. And you can find the BBO version of EvoMol, the BBOMol, in the GitHub of Jules Leguet. And so in conclusion, I will say that when you have a costly objective functions and when you want to generate something, your objective function needs to be clear. And many times we use complex generation methods because we don't know how to ask the problem. And beware of the biases. There is bias from data, clearly, but there is also biases from experts. So depending on what you're looking, and sometimes the chemistry is biased by the chemist also. If you manage to do some synthesizability scores and filtering, EvoMol works great and produce really reasonable and realistic molecules. And if you don't have any data set and you want to try a BBO, I think that it could be a good idea. The problem with the GPR is at the size of the populations, but it's a specific problem. Which method do you use for the GPR? Great question. So we've tried several representations, a subgraph representation called the shingles, or the fingerprints MBTR. I run predictions on mutations that increase distance from the if I'm correct, Jules, the expected improvement is not only the distance from the training set. Depending. So I think that Jules can better answer the question concerning the expected improvement part. If you have any other questions, and I will thank you for your attention, by the way.
Thank you so much, Thomas, for the great presentation. I really like the conclusion. Yeah, the objective function part is something that really hit me. Is the kind of conclusion that I think you share across the globe, like in material design and drug discovery is the same thing. And the bias in the data and all of that, like those are great conclusion. And thank you for sharing all of that. If someone has question, I will invite the person to open their mic and ask. But I go with the first question though. First question. So on the data set that's available, you have said that when you do the DFT, you have seen that a lot of molecules were not stable. With that information available in the data set, because I feel like it's the kind of information that can be used now maybe to build a new scoring function to whether a molecule can be stable or not, given the amount of data that you guys have generated.
There is, for example, the CIBA method that more or less work like something that we've tried. That means that looking at what converged in DFT or what failed, can we predict if a molecule will be stable or not? What we see is that we know that some chemical environments leads to failure in DFT almost certainly. The thing that many times it's combinations of two local environments near from each other that produce tautomery, change in the electronic structure, break of the molecule. And so this is more complex to discriminate 100% of the time. That means that we have seen that when we've produced diversity, it was unconstrained. And we should have used some synthesizability filtering or whitelisting to prevent probably half of the failures with chemical environments that are not possible. However, if you use a descriptor that is really large, that means that, for example, you want a fingerprint with three bones layers, it's so specific that you cannot list them all. So you cannot use them as a whitelist or a blacklist. And when you restrict it, you cannot say this chemical environment does not exist. The thing is that this chemical near another one. And so that's the beauty and the complexity in chemistry.
Okay, I see. Thank you so much. Any other question? People who have asked questions in the chat, if you're not satisfied with Jules' answer, it's time to to ask Thomas again.
You can always find me by mail. If you have a complex objective and if you want to try maybe this objective with EvoMol, we could discuss also. If you, I'm not a drug-like chemist. However, if you have your objective functions and a method to score, it's okay. What I cannot do is answer problems when, for example, let's say I would like this kind of drug, but I don't know how to score it. I cannot answer those problems yet.
Unfortunately, I think like that's the kind of the problem that we have in drug discovery. Like we don't have like we cannot simulate everything. So yeah. And there's a question from Emmanuel. Let's take this one.
Thanks, Thomas, for the presentation. It was very insightful. I have a small question about EvoMol. There are other works that use evolutionary algorithm for molecular property optimization, including the one that you cited from Jan Janssen. So have you compared EvoMol to these other methods? And I know, for example, there's one that tried to apply the mutation space on smiles and not graph. So did you compare to see like which one was performing better in terms of optimization or drug-like of molecule that are produced?
So the answer is no. It's not that we didn't want, it's that we didn't have the human resources, and we always had other things to do. That means that when we built EvoMol, it was planned to compare it to another evolutionary algorithm. But since we've seen that our method works well, we thought it more interesting to try and to stress it, to make it work on problems and to tackle science than to compare several methods. But it could be interesting. By the way, Jensen was a referee of EvoMol, and he asked if we could compare the number of objective calls to resolve, for example, the QED. And we've seen that the number of mutation calls was pretty similar. In GBGA, there is a crossover mutations, and we could expect that maybe it's a huge pathway, that it opens pathways between chemical space. However, in the problems that we've tackled, we didn't see such kind of improvement with the crossover, and the performances between the two are quite similar, and we've never tried a full study of comparison.
If I may, such as with the GBGA of Jensen, we have taken the guacamole benchmark. So we can compare both methods on this benchmark. And in fact, the results are quite similar. Both algorithms are very effective for the tasks.